All right, guys, super excited for this lesson. This lesson is on the derivative, which is our main focus for the first semester of calc, and is the reason we put all that work into studying limits. Okay, so remember when we first began the course, we started by talking about this guy, right? Usain Bolt, who is the world's fastest man over 100 meters. We're going to use a function, this x of t equals t squared, to represent his speed, or sorry, his position over 100 meters. And use that to analyze our rates of change. So remember, we started by tackling average rate of change, which is his speed over a certain time period. And we found that that was pretty easy to figure out. It's essentially our slope formula, right? So that would be f of x1 minus f of x2 over x1 minus x2. So that was pretty easy. And then instantaneous rate of change is what we're interested in. And that's his rate of change, his speed at one specific point or one specific instant, right? So we can imagine that if we put a speedometer on this guy, we wanted to know what the speedometer said at one specific moment. That's instantaneous rate of change. And this was the harder thing to figure out. In fact, we don't know how to figure this out quite yet. Today, we'll learn how. So I want to start by tackling a couple of average rates of change to build towards this idea of this instantaneous rate of change. So we could use either of these averages to estimate this instantaneous velocity, but when we're done, we're going to figure it out exactly. Okay, so here are my solutions here. This should have been easy for you. You're just plugging them into this formula. Make sure you have units if you didn't include those in your notes already. Meters per second for velocity. And then for choice C, or question C rather, you should have said 3, 5 is a more useful interval for estimating his instantaneous velocity at 4 because it's a smaller interval. Or you could have said that these endpoints are closer to t equals 4. That means the same thing, right? So one of the ideas we had from when we first introduced this topic is that the smaller the interval we use, the better the estimate is for an instantaneous velocity. Okay. Now, we're going to abstract this some because we know in math that sometimes when we make things a little bit more abstract, that can give us some insight into the problem. So we want a formula for the rate of change on the interval t plus h. Okay, so that would look like this. X of t plus h, and I'm following just this pattern that I did before, minus x of t over t plus h minus t. The reason I'm using these variables, and particularly t plus h, is I want to represent some t value and then a small change to that t value, right? So for example, t could be 3, h could be 2, right? Because 3 plus 2 is 5. Now look what happens here. So right away, those cancel out. So I can simplify it some a little bit. And then if h represents a change in x, so from 3 to 5, for example, if we want the best approximation for an instantaneous rate of change, h must be small, right? So the smaller this h is, the smaller the change in x is, the better the estimate is. Well, we just spent a whole bunch of time learning about limits, so we actually know how to make h really small, right? We can take a limit as h approaches 0. Right, so we can let h get closer and closer to 0 and see what happens to this function. So if we want an instantaneous rate of change at t equals 4, this is super cool. So we can take the limit as h goes to 0, rather than trying to guess at it now, we can find it exactly, of this expression here. So x of 4 plus h minus x of 4 all over h. Remember now, x of t was equal to t squared, right? So x of 4 plus h means I square that, and x of 4 means I square that. And then we know how to solve a limit like this, right? We simplify it, and we look for h to cancel out so we can substitute in a 0 without having a 0 in the denominator. So when I square that top part, you get 16 plus 8h plus h squared, and please draw the Punnett square if you're not sure how I got that. 4 squared is 16. And look what happens now. 16s cancel out, and I'm left with only terms with h in them. And if I have only h's in these terms, I can pull an h out of each and divide by this h in the bottom to get rid of it. So ah divided by h is 8, and then h squared divided by 8, or by h rather, is h. And then I can plug in a 0 because I no longer have it on the bottom. My limit is 8. This is an instantaneous rate of change. So this means that Usain Bolt at t equals 4 is traveling at 8 meters per second at that instant. And notice it matches up with their estimates, right? So 10 meters per second was a worse estimate than this estimate here, which turned out to be spot on. So our main idea, and this is super important, is to find this instantaneous rate of change. We let the size of the interval, so that's h, or the change in x, go to 0. So that's why we did all that work on limits. Okay, make sure you have the notes, and then we're going to move on. Tell you exactly what the word derivative means finally. So the derivative is exactly what we just did. It's the instantaneous rate of change. It's the rate of change for a function at a specific instant. And that rate of change depends on x. So we're going to have a formula with an x in it. So it changes as we move about the curve. So graphically, this would be the slope of a line that just touches a curve at a certain point. So that's what we're finding when we find the derivative. The way we find it is by that definition we just used. This is called the limit definition of the derivative. So let's find one. Let's use this. F prime, so find f prime of x. That's how you say that. That means the derivative. That's the notation we use. Well, f prime is going to be what we get when we use this definition. We take the limit of the secant line slope as the interval gets really small. So here's f of x plus h, right? I plugged x plus h in, minus f of x. So minus my original function, and I'll put parentheses around it to say I'm subtracting the whole thing over h. Then it's the limit I know how to solve, right? So I squared that. Please draw the Punnett square and work that out if you're not sure how I got that. 3 is just chun, and then I'm going to distribute my negative. And notice there's some terms I can cancel out already, right? So plus 3 minus x squared plus x squared. And then I should be happy because notice everything that's left over has an h in it. And then I can pull an h out of each term just like we did before. And now I can plug that 0 in. And my limit is 2x. So that's my derivative. You just found your first derivative. F prime of x is 2x. Okay, so this is the slope as we move along this function. Notice like the slope over here is negative, whereas the slope over here is positive. Plugging in an x is how we figure that out. So let's find the equation of this line now. So remember we said that the derivative is the slope of the tangent line. Well, in this case, that's 2x, which in this case is 2 times 1. So I plug in that x equals 1, it's what I'm given. So the slope of my tangent line is 2, right? We know an equation for a line is y equals mx plus b. So I plug in that 2. And remember, you know this from your work in your previous math course. So when we're finding tangent lines, we need a point and a slope to find the equation of the line. So my slope is my derivative. My point comes from what's given to me. So I know that this point here is 1 comma something. And I know it's on my original curve. So the way I can find my point, if I have x equals 1, my point is going to be 1 comma whatever my original function of 1 was. So f of 1, well, f was x squared plus 3, right? So my point is 1 comma 4. And then you guys for sure know how to do this. 4 is my y, 1 is my x. So my tangent line is y equals my slope, 2x plus 2. So that would be the equation of this line that just touches the curve at this point. The slope of that line represents the rate of change. Okay. So key takeaway. Make sure you have this definition of the derivative written down. And then the key takeaway here is what the derivative means. So when I say derivative, you think slope of the tangent line. When you hear slope, rate of change, you think derivative.